Welcome back to our videos. Today we're going to learn about differentiation for vector-valued functions. So far we have only talked about functions that map to the real numbers, and today we are going to extend the idea of differentiation to functions that map to a higher dimensional vector space. So that's section 13.4, differentiation of vector-valued functions. Okay, so what we are going to do is we're going to take the ideas that we have developed so far, especially the idea of total differentiation, and extend that to vector-valued functions. And you remember the basic idea here was to locally approximate a function through a linear function. Basically that linear function was governed by one single term, that was a vector g as we call it. That was then the derivative. And of course, we can do the same thing for vector-valued functions as well. We do have linear mappings available for vector-valued functions. So why not just approximate a vector-valued function by a linear mapping? Of course, a vector will not be sufficient to describe that linear mapping, but in general, what we use is matrices, right? In general, linear functions can be described through a matrix in arbitrary dimensions. So we are going to do just that. We're going to replace the vector by a matrix, and then we have extended our idea to vector-valued functions. And it's just as easy as that, really. Okay, let's make a quick note before we actually do that. So the idea of total differentiation can readily be extended to vector-valued functions. We just interpret the differential as a locally good linear approximation, and we just have to come up with a linear approximation for a vector-valued function then. So the idea is interpret the differential as a locally good linear approximation. And this locally good is expressed in the limit condition for the remainder. You remember that, yeah? So the remainder, if we move closer and closer to the point that we consider, the remainder goes to 0, and it goes to 0 faster than the difference of the current point and the point that we considered. Okay, so basically we're going to copy the definition more or less, and just introduce new names here. So that's our definition of differentiability for vector-valued functions. As usual, let x be a subset of R to the n, f a function defined on x, and now we are going to define that as a function that maps to some R to the m instead of just R. And let x be an x star as usual. And we'll define what total differentiability means in that case. And f is called totally differentiable at x star if there exists, and as I said, formally we used a vector. Now we are going to use a matrix in place of that. to get our linear mapping. So if there exists a matrix, we call that matrix JF. That's going to be a matrix with m rows and n columns. And again, we need a remainder function, so and a function r defined on some delta neighborhood of the origin that now also maps to r to the m instead of just r. Defined on some delta neighborhood of the origin 0, such that the following conditions hold. Well, again, f of x is the same as f of x star plus the linear approximation, and now we're taking this matrix JF to do the linear approximation. So it's JF times x minus x star plus the remainder at x minus x star, where the limit as x tends to x star of that remainder x minus x star divided by the norm of x minus x star that tends to 0. And exactly speaking, we would have to use the 0 vector here. So what we're doing here is we're taking the limit of a vector valued function, and well, we defined how to do that. Basically, this is the same as taking the limit of every component separately. So that's it. Basically, that's an exact, more or less exact copy of the definition for the real valued case. And this matrix JF, that has a special name that is called a differential. That's not surprising, hopefully. It's usually also called the Jacobi matrix or Jacobian. And that's, of course, where that J comes from. Okay? The matrix JF is called the differential, the Jacobi matrix, or the Jacobian of f at x star. It is denoted by, well, either JF, as we just had it, often JF at x star, if you want to mention the point, or again DF at x star. Sometimes, but less frequently, also F prime at x star. Okay, so that's a straightforward extension. I need to mention one thing here. I already mentioned that in one of the last videos. To be consistent with this definition, it is important that, of course, the case m equals 1 is included here. Yeah, so if m equals 1, then we're back to the real valued case. And you remember in the real valued case, we just took a vector here for that JF. Now this JF for m equals 1 is formally a 1 times n matrix, so that vector needs to be a row vector. And that's why I insisted on the differential being a row vector, whereas the gradient is usually written as a column vector. Okay, so you remember I said gradient and differential are basically the same, with the exception of transposition. And that's basically where this comes from. these two definitions need to be consistent, and so we write the differential as a row vector, even though the gradient is usually a column vector. Okay, it's basically just by convention. Okay, let's make a quick note of that, so that hopefully you don't forget about that. So for consistency with this definition, we will regard the differential f prime of x star for a real valued function f x to r as a row vector, or in other words, a 1 times n matrix. Okay, so strictly speaking, and from now on we will use that convention strictly, f prime of x star is not equal to the gradient, but to the transposed gradient. Okay, so that's the definition. For practical computation, what we will usually do, what you can do is you can regard a vector valued function as just a vector of real valued functions. And of course, for these real valued functions, we already know what to do. You can compute the total differential through doing the partial differentials. So what if we just did that? Does it work? And of course, it turns out all of this is in fact consistent. That does work. So we can just regard a vector valued functions as a bunch of real valued functions, then do the computation for each of these, and then combine it all to a big matrix, and that's going to be the Jacobian in the end. So write that down as a theorem before we then see an example of how to apply that. So a vector valued function can be regarded as m distinct real valued functions and fortunately our definitions remain compatible with that viewpoint. So we'll write that down as a theorem that basically tells us how to compute the Jacobi matrix. So let X be a set in R to the N, be open, F a function on X to R to the M with F of x1 to xn being the vector f1 x1 to xn to fm x1 to xn. So we have m distinct real valued functions. For suitable functions, fi to fm defined on x, mapping to r. And the function f is then differentiable at some point if all of those functions, and only if all of those functions are differentiable at that point. And we can just get the Jacobian if we compute the differential for each of those functions and then put all of these together in a matrix. So the function f is differentiable at some point x star in x if and only if f1 to fm are all differentiable at x star. And in that case, the Jacobian can be easily computed. The Jacobi matrix of f at x star is determined by, well, jf at x star is then simply the matrix made up of the differentials of the component functions. So f1 prime of x star, remember that is a row vector, so that's the first row of the matrix, to fm prime at x star. So we just take those differentials, put them as rows of a matrix. Or you could just say what we're doing is we're differentiating the ith component function with respect to the jth coordinate, so dfi dxj. And we're doing this for all rows I from 1 to m and all columns j from 1 to n. And this yields an m by n matrix, and that is the Jacobian. Okay, so pretty easy. Let's do a quick example to see how this works. We'll start with a function that maps from R2 to R2. We'll define that function as f of x1, x2 equals, let's say, e to the x2 and x1 e to the x2. So that's a function that takes two variables as input and outputs a two-dimensional vector. So to compute the Jacobian of that function at some point x, what we have to do is we have to differentiate first the first row. So let's start with that. Start with the first row, this function here. In the first column, we differentiate with respect to x1, so that's 0. In the second column, we differentiate with respect to x2, so that's e to the x2. And then for the second row here, again, we differentiate with respect to x1 first. This is e to the x2. And then with respect to x2, that is x1 e to the x2. Okay, so that's the result here. And remember, this first column is made up of the d of the fi dx1. That second column is made up of the dfi dx2. So in the columns, the coordinate that we differentiate to, that is a constant. Whereas in the rows, we always differentiate the same function. So this row consists of df1 dxj. and this row here consists of df2 dxj. So basically you just differentiate the rows, each row by themselves, and that's it. Okay, and of course we can write this a little more easily in that way. E to the x2, we can factor that out. 0, 1, 1, x1. Okay, so that was the first example. Second example, a special case. Of course, we don't need to have several variables. We can also regard functions of one variable that have a vector value. So for example, if we look at functions like this, from 0 to infinity, so from a real parameter mapping to R2, and you might remember that we call these curves. So that defined as t cosine of t, t sine of t, like this. Then what is the Jacobian of that at some point t? Well, this time we get two rows, but we'll only get one column. So what we do is we just differentiate each of the rows as a simple one-dimensional function. And that will give us, using product rule, we need to differentiate t cosine t, that is cosine t, plus, no, minus actually, minus t sine t, because the derivative of the cosine is minus the sine of t. And for the second row we get sine of t plus t times cosine of t. Okay, so in this case what we get is a 2 by 1 matrix. And that's the derivative, the differential of this curve here. Okay, there's going to be more examples in the exercises, so have a look at the new exercise sheet. See if you can do this for yourselves. It should not be too troublesome, hopefully. So, thanks for your attention. I'll see you in the next videos.